Well, good morning, or good afternoon, or good evening, whenever you're watching this. This is the first of many videos of mine that you will watch this year. This one is on limits. Now, limits are a concept in calculus that you will need to know in order to understand concept better as a whole. So, we're going to start by talking about limits. And what a limit is kind of looking for a pattern. You're looking at what happens to the y value of a function as the x values get closer and closer to a very specific number. So let's look at an example of that. Let's look at a very easy function, f of x equals x squared, and we're going to look at what happens to y as x approaches a value of 2. So what I want you to do is I want you to grab a calculator. If you don't already have one with you, then you'll be able to pause and grab a calculator. And once you have that calculator, type in the function f of x equals x squared, and have a look at the table and have a look at the graph near x equals 2. For your table, I would suggest you look at numbers like 1.97, 1.98, 1.99 on one side of x equals 2, and then on the other side, look at numbers that are a little bigger than 2, like 2.01, 2.02, and 2.03. So pause the video and type that into your calculator and see what you notice. All right, here's what you should have noticed. When you type in numbers like 1.97, 1.98, 1.99, you should get numbers like these. And I'm kind of writing over them, but you get the idea. And when you choose numbers that are a little bigger than 2, you should get numbers like these. So what you're noticing is, as you get closer and closer to x equals 2 from the left, numbers a little smaller than 2, and as you approach x equals 2 from the right, using numbers that are a little bigger than 2, you get y values that are equal to or getting closer and closer to 4. Same thing when you look at the graph. Here's the graph of y equals x squared. And looking at the y values as I approach an x value of 2 from the left, I'm getting gradually and gradually bigger. And as I approach x equals 2 from the right, my y values are getting a little bit smaller and a little bit smaller, and they kind of meet at a y value of 4. So that was kind of an easy example to start with. So the strategy here is, if you have a nice easy function like y equals x squared, what you can do is you can just substitute that x value right into the function. Okay? And we were able to do that with this function because it was very easy. We were looking at the function y equals x squared, and we were looking at what happens as x approaches 2. So just go ahead and plug the 2 in for x, and you should get 2 squared, which is 4, a y value of 4. All right, easy enough, right? Then we get a little bit tricky, looking at an example like this one. We've got a function x squared plus 5x all over x, and we're looking at what happens to y as x approaches a value of 0. Okay, so if we use our first, the first strategy that I mentioned, which is just plugging 0 in to the function, then I would get 0 squared here plus 0 here all over 0. Well, that's not good because you get 0 over 0. So we're going to have to go back to what we did on the first example, and we're going to have to plug it into a calculator. Take your calculator and plug in the function x squared plus 5x all over x, and make sure you're using your parentheses and fractions properly so that the function looks like it's supposed to. And look at the table, sorry about that, look at the table and the graph near x equals 0. And pause the video, do that, and we'll see what happens. All right, and this is what should have happened. We've got values that are closer and closer to 0, but just a little bit less. So we call that approaching x equals 0 from the left. And then we've got x values that are getting closer and closer to 0, but are a little bit bigger. We call that approaching 0 from the right. And if you look at these values, they get closer and closer to a certain number, and that number is 5. But notice that the function doesn't actually exist at 5, okay? Because when you plug x into, or if you plug 0 in for x, then you get a y value of 0 over 0, which is indeterminate. But these numbers do get closer and closer to a y value of 5. And it actually looks like a straight line like that. And because 0 is the only place where this function doesn't exist, we just put a hole right there in the graph. Your calculator probably wouldn't do that. It likes to connect everything. So you'll probably on your calculator see just a straight line, but just know that that's incorrect. All right, so if I try and substitute and I get an error when I'm doing that, something I should probably try is to factor the numerator and the denominator completely. All right, so looking at the example that I had, this is what I had originally. I noticed that I can factor an x out of both terms in the numerator, giving me x times x plus 5. And the bottom is factored as much as it can be. So that's what I have, x times x plus 5 all over x. You see a common factor of x on top and bottom that you can cross out as long as x is not equal to 0. That's a very tricky concept to understand, but realize that x is not equal to 0. X is approaching 0. So x is taking on values that get close to 0 but never actually get there. So it is okay for you to cross out these x's because they aren't technically equal to 0. They are just close to 0. Okay? So if I cross out those x's on top and bottom, I get something that looks like x plus 5. So now this is a function that is similar to the one that we started with, and I can plug 0 into this. And when I do, I get a y value of 5, which is kind of what I saw in the table. All right, I'm giving you an example to work through. So here's the example. Pause the video and work on this example, and we'll see what you get. All right, so let's look and see. I gave you something that was factorable on purpose. So the top can be factored into x plus 2 times x plus 3. I'm looking at x as it approaches negative 2. I can only cross out the x plus 2's if they are not equal to 0. And that only happens at x equals negative 2. But remember what I said before, x is not going to equal negative 2. It's taking on values that are close to negative 2, but not actually there. So I can go ahead and cross those out, and I'm left with a function of x plus 3. And that's something that I can plug negative 2 into, and I will get a y value of 1. All right, now this next thing can happen. Sometimes the limit doesn't actually exist. It will only exist if you notice a pattern when you're approaching the x value from the left and from the right. If you get closer and closer to the same y value, then the limit exists. But if you get different y values, if you're approaching from the left and from the right, then the limit doesn't exist. And I wanted to give you an example of how that would happen. So here we're finding the limit as x approaches 0 of the absolute value of 2x all over x. All right, using previous strategies, I can't factor that, and I obviously can't substitute 0 in for x because then I get 0 over 0 again, which is indeterminate. So I've got to go back to just looking at what the graph or the table looks like. And this is what they look like. So notice that as you approach x equals 0 from the left, meaning I'm using numbers that are a little bit less, I consistently get a y value of negative 2, which means that as I approach x equals 0 from the left, I get a y value of negative 2. The limit is negative 2. And as I approach x equals 0 from the right, I consistently get y values of positive 2. And if you graph this on a calculator, you're going to get something that looks like this. Okay, so there's this big jump from all of these negative 2's to all of these positive 2's. So as I approach from the left, I get a y value of negative 2. As I approach from the right, I get a y value of positive 2. Those are different. So what that means is the limit doesn't exist at x as x approaches 0. The limit does not exist. And you can say that. Sometimes that happens. All right? Excuse me. So I'm giving you 12 questions based on this graph here. And I want you to see what you get. This little minus sign here, let me just show you. This little minus sign here means you are approaching from the left. And this little plus sign means that you are approaching from the right. And if there's no sign there at all, that means that the limit will exist only if the left-hand limit and the right-hand limit are approaching the same number. So keep that in mind when you're doing these questions. Pause the video and resume the video once you have all 12 questions answered. All right, looking at the answers. Looking at the answers. There we go. Okay, as I approach -1, here's x equals -1. As I approach from the left, I'm getting closer and closer to a y value of 1. And as I approach x equals -1 from the right, I'm getting closer and closer to a y value of 2. And since those numbers don't match, the limit does not exist. Looking at what happens as x approaches +1, here's x equals +1. As I approach x equals +1 from the left, I get close to a y value of 2. As I approach x equals +1 from the right, I get a y value of +2, or I'm getting closer to a y value of +2. Those numbers do match, so my limit is +2. All right, looking over here at the last 6 questions. As I approach x equals 2 from the left, I get closer and closer to a y value of 5. And as I approach x equals +2 from the right, then I get closer and closer to a y value of 3. Those numbers don't match. The 5 and the 3 don't match, so the limit does not exist. And then looking at what happens as I approach x equals 4 from the left, I get closer and closer to a y value of 3 again. As I approach x equals 4 from the right, I get a y value of 3 again. And since the left-hand limits and the right-hand limits match, my limit does exist and it's equal to 3. So that's limits. Please email me a question on anything you've seen in this video. Not a lot of real-life applications to this, so I know I'm going to get that question a lot. But it will lead up to a very important concept in calculus. So just be patient, and in a couple of lessons, we'll be at the main crux of what calculus is all about. So I look forward to seeing you tomorrow.